So I'm Miroslav, as Lizette introduced me, working as a postdoc here. So it's my pleasure to introduce Leonie's talk, who will give us a talk on the topic of network inequalities, more precisely from network interventions to systematic errors. She'll say more about that. I'll just briefly introduce her career. She did her PhD and she worked in the group of computational network sciences at Aachen University. But afterwards, she decided to continue in academia, right? And now working at Environ, which is a German electricity transmission company. So she probably applies her previous knowledge gained through her studies in the industry. So it's a pleasure to have someone also from not in the academia to give us some of his works and maybe to provide some further insights that is gained after obtaining the PhD. And yeah, we have time for 1 hour in total we have, including the questions. We will leave the questions at the end because of the recording. I know it's healthy to have the discussion, but if it's really not very urgent for the sake of the understanding of all of us, I would ask you to have the questions at the end so people afterwards can follow the recordings more easily. The floor is yours, Leonie.
Thank you. So first of all, thanks a lot for inviting me. I'm super excited to be here today. Also, I just told that one of the papers I will present here I actually wrote here when I was here 1.5 years ago, and I said it would be amazing to come back to present at work again, and so now I'm here. So this is like an additional pleasure. And I will generally talk about, basically it's like my PhD was a bit split in half. I was doing a lot of groups and networks, on the one hand on group interactions network, and the other half is more on like attributed networks and inequalities. And I will present 2 papers from my PhD today, which are broadly about network interventions and systematic errors. And to start this talk, I just want to generally set the scene with my motivation I have, especially for this like general area of my work. And this motivation comes from the fact that I think we live in a very diverse world. We have like a very diverse workforce nowadays. Like we have people from all different kinds of backgrounds, different kinds of gender. And I think this is reflected in many parts of the society. But, and this is a big thing, most of the top ranks of a lot of places in this world still look a lot like this, which is like the contrary of diversity, I would say. This is I know who of you knows this picture. It's a famous picture from the CEO meeting of the Munich Security Conference in 2022. So think about this picture, what you want, but it definitely doesn't reflect the general population that looks more like the fact on the right. And of course, there's a lot of issues that play into this, and I won't be able to talk about all issues that lead to these factors today. But one thing that I think that is super important is that if we look at society, visibility of minorities is an issue. Like we don't always have the full picture of all diversity that there actually is. And this is even enhanced nowadays in social networks, because if you have an online presence, or if you generally have an online reflection of the world, like for example in this case LinkedIn, and then you search for something, you get search results that are ranked in some way. And like in this case, for example, you have a ranking of chief executive officers that you search for, and 3 of them are males and 1 is a female. So basically, you have this ranking that comes from it, and there's 25% of women in the top 4 results. What does this tell us now? Does it say that like the underlying population of the CEOs generally that are on LinkedIn are also 25% female, or is this just a reflection in the top ranks of the system that is in some way biased? And these are questions that I found super interesting because it just shapes so much how we see the world and how we also perceive different groups in this world and in influential ranks of decision in our world. And as I've already said, there's a lot of different things that play into this, but I want to give you today a specific perception on inequality, which is a network perspective. And for this, think about the fact that if you have two groups, for example, a majority and the minority size and the general population is 10%, then these are generally macroscopic measures of just group sizes. If you now have two networks of interactions between these groups or people of these groups, we already see that the nodes are like different sizes. That's ranked by degree centrality. So larger nodes have a lot more connections to other nodes than the smaller ones. And we see that from these macroscopic measures, we can generate very, very differently looking networks that then also create very different network measures. For example, here in the degree rankings, you see that in the left network, there's a large overrepresentation of the minority in comparison to the 10%, which is the global population, in comparison to the degree ranking on the right, where basically there is no minority present in the top ranks at all. And I mean, this is not 10 nodes, but still, if you look at the network, it won't be there for a lot of these top ranks. So what we can generally see from this is that the network structure really impacts a lot the visibility of minorities in networks. And for that reason, it is super interesting in this inequality research world to look at networks and specifically to also look at the fact how group membership can actually impact the structure of a network. Because if the structure impacts the visibility of minorities, we also have to see, is there some kind of effect of the group membership on the structure of a network itself? And in my thesis, and also what I wanted to present you today, I looked at this in two different ways. First of all, the group membership can impact the growth of a network, the structure of a network through growth, through the attachment of new nodes to a system. And then also in the linked documentation process, we know that normally the things that we look at, the data that we process, is not error-free. There's all kinds of linked documentation errors, and these can also be impacted by groups in a network. So systematic errors can occur in the structure that then in the end impacts the network structure and therefore also minority visibility. Let's go into this right case first. And to give you the motivation behind the first work that I want to present you here, I want to go back in time with you to more or less the year 1900 in Germany. And in these days, this is an example of a board meeting of the Krupp AG in the early 1900s. The executive levels looked pretty much like this. And that's no surprise because also the workforce, was not that diverse, at least not as today. So like this ranking result basically in the top ranks of the system in the 1900s is not really a surprise. However, over the time, more and more minority members have entered the workforces, but as I've already showed you in the beginning, there's basically no change in the top ranks of the system. So what we can draw from this is that just simply increasing the size of a minority group cannot only be the only intervention to combat inequality in terms of visibility. And there's a lot of things in terms of interventions that have been tried to actually increase minority visibility, to come from there to there. And first of all, there's a lot of group size interventions. Like we summarize this with the term of group size interventions. You can think of things like affirmative action policies or quotas, like just simply things to increase the size of a certain group in a system to maybe make that group more visible. There's also a different, flavor of interventions that are around that we summarize under the term behavioral interventions. That is more like, for example, creating networking opportunities for minority groups. So change the interactions that groups have with each other. Or for example, just the tendency of leaders nowadays recognizing that having diverse groups is actually a good thing. Like it actually increases productivity, it's a good thing for example, in companies. So these would be behavioral interventions where you change the way that people interact with each other and not simply the size of a group. And our goal in this work was to model different kinds of network growth interventions that fall into these two categories and see how does this actually increase minority visibility. Is there like a clear trend that one of these types of interventions is better than the others? Are there any kinds of interaction effects? So to actually check from a network theoretic perspective, how effective are these kinds of interventions? So for this, we first of all have to look at the fact of how, or the question of how networks grow. And there is a really nice work that probably most of you are familiar with here from Cavini et al. That is the Arabashi-Albert homophily model. And this growth model, this network growth model, basically has a growth mechanism with a probability that a new node connects to a network according to this probability there. And basically, there's two factors playing into this. First of all, preferential attachment, and the preferential attachment mechanism is this mechanism of the rich get richer. So basically, if you have a high degree as a node and you have a high rate of attachment, you get more popular more quickly. And if you have a low degree, then you have a low rate of attachment. This is one mechanism that we know that exists in growing social networks. And there's a different flavor that this model adds to this world of growing networks, which is the aspect of homophily. And homophily is a mechanism that basically says if you are in a group, you might have a homophilic tendency to only connect to people of your own group or have a preference for that. And if you rather are in a heterophilic state, then you might have a tendency to rather connect to people of a different group. And these two factors together, if you generate networks from that, there's a very interesting thing that the authors found. So here are two different networks that are created with this model. One is heterophilic and one homophilic with a minority size of 20%. And if you create degree rankings from these networks, then we see that according to the expectation in rankings, if you have like the top D% here on the x-axis, which would be 20%, in heterophilic networks, in the top ranks of the system, there is a large overrepresentation of the minority nodes. And in homophilic networks, there is a large underrepresentation of the minority nodes. And you can actually write this down as a function. So the visibility of minority group actually is a function of their relative group sizes and their homophily. So these two aspects really shape how we see minority nodes in networks that are shaped this way. So now the question is, how do interventions impact these structural inequalities? And to look at that, we adapted this growth model into a two-phase network growth model. So basically, we have a first phase where there is newly arriving minority nodes, and not only minority nodes, generally arriving nodes. And here there is an example of a 10% minority in the first phase. So there's just the usual attachment mechanism here. There's the example of the heterophilic attachment in the first phase. And this happens up to a point of a network growth intervention. And then two things can happen. First of all, there might be an increase in the number of minority nodes in the second growth phase. So here from a 10% minority to a 19% minority. So this is not actually a minority anymore in the second growth phase because the quota in this case would be such intense. So then you would end up with a final network with a 50% minority because of course those nodes were already there. And this would mimic a group size intervention in that case. Another thing that can happen is that you have a change of behavior of attachment. So the behavior of the attachment could change from heterophilic attachment to homophilic attachment in the second phase. And if then the group size doesn't change, you still end up with a final network of a 10% minority, but you have this behavioral interventions of nodes attaching to the system in a different way. And of course, you can combine these two different worlds in any kinds of interaction, however you want. So, what kind of results did we find from these interventions that we model? To look at the visibility of the interventions, of the minority nodes in these interventions, we basically compared the minority fraction of the nodes in the top 100s from the pre-intervention ranking, so the point of time when the intervention happened, to the post-intervention ranking. And then also we compared this to the minority fraction in the total number of nodes, because that would be kind of the expected value that you should see in the top ranks. So let me walk you through these plots. What you see here is the simulation results for a pre-intervention setting that was homophilic. I will show you the heterophilic later, but this is only homophilic pre-intervention setting. And on the x-axis of all of these plots, you see a shift from heterophilic to homophilic attachment in the second growth phase. And from the left to right in these different plots, you see a raise in quota from 10%, so here nothing happened basically, no group size intervention, to 90% quota, so an incredible amount of course, realistically, not very realistic, but in these simulations, just to make the point, a 90% quota in the second phase. This dashed line is a proportional representation because you always add more minority nodes to this quota. Of course, the proportional representation is higher in each plot. And this dashed line here is the pre-intervention ranking representation before we apply any kind of intervention. And what you see in these plots is super interesting. Actually, there is an interaction effect between quota and behavioral intervention, because for very small quotas here on the left, heterophilic attachment becomes more beneficial for the minority to increase their representation, and nothing at all happens for homophilic attachment. Whereas for large quotas, and remember this 90% is a crazily large quota, you have to basically adopt homophilic attachment as a minority to do anything at all at your representation. So basically there is this homophilic attachment that has to be adopted for a minority with increasing quota to be able to advance their position at all. And just to make this a little bit more clear, look at this, like this is a 70 and 90% quota, that's really, really high. But if the minority doesn't adopt homophilic attachment and stays with the heterophilic attachment, they don't advance their position at all. They even lower it here on the right, which is, at least for me, was counterintuitive in the first place when I saw these plots. Okay, but can we explain this? Like, why is this the case? And to explain this, we looked at the degree distributions of the post-intervention nodes. And here you can very vividly see that basically the degree distribution changes. We have like this role change of the minority for larger than 50% quotas forming the numerical majority of the newly incoming nodes. So then also just these newly incoming nodes, basically you have the degree distribution of the majority forming the large degree nodes in the second phase. So that's why also if you look at the degree growth, there's only a shift in the degree growth of the minority nodes if you actually have this right tactic for the numerical majority or minority in the second phase. And if you don't attach this favoring behavior, then you don't see an increase in degree growth of the minority nodes at all. So basically, you only see this intervention effect on the degree growth in a case where the group size and behavioral interventions are coordinated. So the main thing you should take away from this is group size and behavioral interventions cannot really stand side by side, but they really have to be coordinated to be effective in terms of minority visibility in the top ranks of the system. And there's one other thing that I want to highlight. Now I added two different pre-intervention settings. So this was only the homophilic pre-intervention setting. This one is now also the neutral and the heterophilic one. And because heterophilicity was more advancing for minorities in the first place, of course, these ranked representations are a lot higher. And what you see is that if you look at the proportional representation for intervention settings, pre-intervention settings that are homophilic, it is super hard to reach this proportional representation only through forward-looking interventions. So sometimes you need to change something at the network level in general to have a different starting point. You cannot only do forward-looking simulations, even with very intense quotas, because you won't have any chance to reach this proportional representation only from that baseline. Okay, so this has been purely simulations to understand this mechanism better, but what we also did is we did some simulations on real-world data. We took the scientific collaboration network of the American Physical Society co-authorship network, and you see the stats of this network here, and you see that there's basically from between 1940 and 1970, there hasn't been an increase in a minority at all, just very, very slightly. And what we do now is we simulate interventions on this original networks every 10 years. So we basically assume what if would have happened if there would have been an intervention in 1940, what if in 1950, and so on. And we compare the effects with the actual network, how it developed. What's the results of this? So if we look at a setting where we don't imply a quota, so we just take the actual minority sizes, each of these intervention steps, and we only simulate behavioral interventions. And what you see is that the most beneficial attachment mechanism here, like in the simulations before, is heterophilic attachment. So heterophilic attachment here advances the minority a lot. Neutral or homophilic attachment doesn't advance it at all because it stays the minority, like there's no quota implied at all. So if we now simulate a case where we always apply a quota that is big enough such that we will have equity in the end of this 10-year simulation framework, so 50% final minority size in the end, you see exactly the same effect like in the simulation before, that now homophilic attachment becomes the way to go for a minority to actually increase their visibility, and heterophilic attachment actually doesn't really do them good anymore at all. So, summary, what do I want you to take away from this paper? We introduced a two-phase network growth model to simulate group size and behavioral interventions to see the interaction between those two kinds of interventions. And we also, I didn't show you that, but if you read the paper, we have analytical derivations for all of that. So you can actually find the theoretically optimal combination between the two types of interventions that will actually advance the minority most. And something that I still showed you in the end that is important to remember, I think, is that the possibility of reaching proportional representation at all is very hard if you have an initially homophilic setting, even if you imply the perfect combination of these two types of forward-looking interventions. But generally, I think this is like the catch-22. It's very important to think about the mechanism that group size and behavioral interventions are actually interdependent, and they have to be coordinated, or they will have no effect at all from a network theoretic perspective. And I underline this from a network theoretic perspective because, of course, there's all different kinds of advantages of different intervention methods, like creating a sense of belonging, etc., that are like purely for itself speaking very beneficial. But in the sense of a network theoretic representation, it really has to be coordinated, or it will have no effect. Okay, this is the paper. Actually, I wrote this paper together with Fadi Van Yang here from CSH and Markus Schumacher and Michael Schaub, and it was actually one of my favorite papers in my PhD. So I really enjoyed this, thanks to my collaborators in that sense. But I wanted to show you a little bit of a different flavor as well, of a different paper that I wrote during my PhD, that is not that much about interventions and growth, but more about the world of linked documentation and systematic errors, because it's great that we analyze networks that like grow in a way, we have like a network there, but we know that like the network we see is very, very error-free. You all work with data, you all know how messy data can be, and there's all different kinds of errors, like measurement errors, data collection errors, but also errors that are made by people, like reporting biases, social desirability biases, that come into the collection of network data that then gives you an observed network with which you do network analysis and node rankings and so on. But like the question is, was the network that you calculated in the first place or that you derived in the first place, is that even reliable? Or how reliable are the results that you get knowing that you have these kind of biases in the process? So basically the question is, what if edges are missing? And the additional question that we pose, because there's a lot of work on looking at what if edges are missing uniformly at random, like what if you drop edges just uniformly at random, but what if there is systematic noise? What if there is noise that is actually dependent on groups, for example, in the network, or also on the position of edges in a network that are not just uniformly at random? I want to give you an example. I'm from Cologne, and I really love Cologne. I don't know if anybody of you knows Cologne, but there's a lot of carnival celebration, and especially in this carnival celebration, there's two groups that don't like each other at all. So there's Kölner and there's Düsseldorfer, don't like each other at all. And if you have maybe like a network of a group of Kölner and of Düsseldorfer, it will probably show up a little bit like that. The question is only, is it really the real network, or is there maybe some kind of reporting bias that Kölner don't want to say that they actually hang out for carnival with Düsseldorfers? like they did that, but they won't report it. Like, is this really the network that is realistic, or is there just an under-reporting that is dependent on the two nodes that are the neighbors of edges because they are not from the same group? And we call these kinds of systematic biases, we developed a model for it, and we call them node attribute-based noise. So basically, the fact that an edge is missing is dependent on which groups are the neighbors on this edge. And there's different kinds of noise that you can imagine. In this case, there could be intergroup noise, so the probability that edges that are from different groups, that those edges are missing is higher than if they're from the same group. Then the opposite is maybe socially desirable to always just say, hey, I'm in contact with the other group, but not with my own one. That would be intragroup noise. And then there could also be the fact that there's simply one group that gets underreported. So if one of the neighbors of the node is from the majority group, it gets missed more easily. That would be majority noise, or minority noise, the contrary. So that's the first type of systematic noise that we consider. And there's another type of systematic noise. And for this, I want to give you the example of scraping Twitter networks. I'm pretty sure it's the same with X still, but like this work was actually still on Twitter. And there's this work that found that this Twitter search API actually overrepresents the more central users and is a little bit fuzzy in the periphery. So the more central a node is, the better it gets represented in the network and like more explicitly scraped in comparison to the peripheral activity. And this is an example of a type of noise that actually depends on the position of the edge in the network. And we call this network structure-based noise. So for example, in this Twitter case, this would be a centrality noise. So the probability of an edge being missing is lower if you are a very central node, and it's higher if you're in the periphery. A different interpretation of this could be social desirability. So you might remember contacts with a very famous central person more than with somebody from the periphery. And another noise that we look at is, we call this Jakar noise. So how high is the neighborhood overlap of the edges that you look at? So an interpretation of this could be availability bias. So if you're in large contact with the same kind of groups and like you kind of have your friend is the friend of the friend and a friend, and you kind of remember all of these people very vividly because you're in large contact, you have a large neighborhood overlap, then these edges might be better represented than if you don't have that. So with these different kinds of models, different kinds of systematic noise, we now introduce this systematic noise model where we either can simulate just independent uniform noise, so we drop edges uniformly at random, or we have this node attribute-based noise, or we have an edge position-based noise. And to see if these different kinds of noise have an impact on visibility of minorities, we do the following in our experiments. We generate some networks with a varying homophily and a minority size of 10%. So we use the Barabashi-Albert homophily model that I introduced before. We simulate errors on top of these networks. And then we get degree rankings from the resulting networks and look again at the minority fraction in the top 100 nodes of the system to see if these errors had an impact on the minority representation or not. So let's look at the results. We start with node attribute-based noise. So you see the different types of noise up here. The blue one is the uniform noise, just to see if there's like non-systematic noise, what kind of influence that has. And we have a heterophilic, a neutral, and a homophilic network. And on the x-axis, you see the retained parameter, which means that basically more edges are retained for 0.8. So 80% of the edges are retained here, 20% of the edges are retained here. So basically, we have a higher noise level to the left of the plot. And I think what's the most important takeaway from these plots is when minority visibility is very, very, very sensitive in heterophilic networks with respect to all the different kinds of noises. And actually the noises also impact the way if a minority is higher visible or lower visible. It can go both sides basically in a very heterophilic network. Whereas if you look at the homophilic networks are incredibly stable in terms of the network measure of minority representation for all different kinds of noise. So like you see a little bit of a change here, but only if 20% of the edges are retained. I mean, that's an incredible high level of noise if you think about it. And the rest is super, super stable in terms of this specific measure that we're looking at. And we actually reproduce this effect on different types of real-world networks. These are ordered by the level of homophily. Of course, it's not like 20, 50, or 80%, but they are like ordered from left to right. This is pretty heterophilic, and you see a similar degree of noise impact like in the plots before. And the GitHub and the APS are rather homophilic, not as homophilic as the network that I showed you before, but we kind of see similar effects. Or like one thing that I wanted to point out, if you look at the uniform noise, well, it doesn't have any impact basically. So uniform noise does not impact these measures or hardly impacts these measures, whereas systematic noise does. And here it's basically the same. Uniform noise does not impact these real-world networks either, but the systematic noise does, at least for the interpreting ones. Last results on the structure-based noise. These results were quite boring, to be honest, but also interesting. So the structure-based noise, at least on the Barabasi algorithm homophily networks, which might be because like the degree distribution is like quite extreme for these kind of rankings, but you hardly see any impact of the structure-based noise in these kind of networks. You see some impact, but like not comparable, at least, to the attribute-based noise. Okay, conclusion. So systematic errors, we try to model these systematic errors to account for errors that are not just uniformly at random, but either depending on the X position or attributes that are in the network. And we actually find also here an interaction effect of the underlying network structure and the effect of the systematic biases, so that in homophilic networks, you have a lot more stable ranking results than in heterophilic networks if you consider some kind of noise. And you can generally say, that this is like robust to all kinds of homophilic networks, also in real-world networks. And what you can do with it, I think this is an important thing because, of course, we haven't like inferred anything because it's very hard to know like what's the ground truth of the network in general. But what's really nice about this simulation framework is to do hypothesis testing. Because if you have a certain data set and you actually assume that there might be some kind of social desirability bias or there might be some underreporting probably between two different groups, you can just use this model to simulate all different kinds of noise levels and see how robust, how much do the network measures that you draw from this actually change with respect to this kind of noise. And for that, do robustness checks of the stuff that you derive from your networks. So this was a paper that I brought together with Felix and Florian and Michael and Markus in 2021. If you want more details on this is the reference. I hope that you enjoyed looking at the effect of groups on either interventions, and I just want to give you the main results again that you should maybe remember from this talk. So group size and behavioral interventions really have to be coordinated to have an effect on minority visibility. And in the world of systematic errors, we found that group-dependent noise can actually alter network analysis results a lot when uniform noise does not. And also this depends on the underlying homophily of a network. And just generally the message and the conclusion, if we want to change towards the future and have more minority visibility and networks, we should really look at these systems from the lens of network analysis because it can explain a lot of underlying structural inequalities that you wouldn't see from a macro perspective if you just look at the numbers, macroscopic numbers of the groups. And to end with, I really want to thank all of my collaborators. It's, as I said, like these were the favorite papers from my PhD, and that's not only because of the topics, but also the people I worked with on them. I really enjoyed this. So thanks to Adi Bayan, Felix, Florian, Markus, and Michael. And if you have any questions, let me know.
Thank you for your great meeting. Okay, so now we can go on with the questions.